Hello everybody, welcome to Physical Science today. We are going to talk about the kinetic theory. And the kinetic theory is a theory that describes the nature of matter on a molecular level. So when you say molecular level, you're talking about when you get down and if you were the size of the molecules and you could see what was going on. That's the molecular level, really small. Okay, so kinetic theory, you guys remember what kinetic means? Kinetic means movement, right? So movement. So if we're talking kinetic energy, which we will in the second semester, will be the energy of movement. Potential energy would be then energy of position. So in the kinetic theory, we have the particle model is another way to talk about it. So we're talking about the particles. All matter is made up of particles. Okay, so when this theory started, that was just an assumption. Somebody said, hey, we can break things down into small little pieces, and those small little pieces are particles. Now we can actually see some of this stuff. Well, we can't really see it, but we can see how it affects electrons. So we'll throw electrons at this stuff, and the way it bounces off or deflects gives us the idea of what's there. So a little note for you, so now we can kind of see this stuff by throwing things at it and seeing the way it bounces off. Just like, for instance, if I couldn't see something, but I knew that I was throwing something in this way, and I had some kind of, shield around the situation, and I could tell that this bounced because I see a little bright spot right here, then I could say that whatever I hit in here that I didn't see was in that direction. Does that make sense? So that's the way we get the shape and the understanding of these really small things that we can't actually see. We start throwing charged particles at it, and then the way they kind of bounce off describes what they look like. Okay, so the particles that we're talking about here then are going to be molecules, and molecules are made out of atoms, or atoms too, molecules or atoms. Okay, so another kind of way to look at this is as far as evidence that everything is made up of particles. When you take and dissolve sugar in water, do you still taste the sugar? Yeah, you still taste it. It still tastes sweet, right? So somebody said, hey, that's evidence right there that this sugar must be made out of small particles. Because when they put it in water, it dissolves, you don't see it, but it's still there. So it must be made out of small units of sugar, basically. Does that make sense? Okay, if there's any questions, let me know. The second part of this model is there are spaces between the particles. Okay? And when you think of diffusion, then that is kind of evidence that, hey, there must be spaces between particles, because when things diffuse, they kind of slip in between other particles. I'm going to show you a couple examples of that here in a little bit. But I see you're all busy writing these notes, so I'll keep talking while you're doing that. Another particle part of the model is these particles are moving. And how do we know that these particles are moving? Well, diffusion is evidence of that. Because if they weren't changing position, we wouldn't have diffusion. So these things are all the evidences related to this particle model. And there's other evidences too. The higher the temperature, the faster the movement. And the evidence of that is the rate of diffusion. So when you see the word rate, that means per time. So when we get something hotter, the particles move faster. Diffusion occurs faster. And then this number 5 here, I want to look at a little bit more closely. This gets down into a little bit understanding of the math. So a more massive particle, oops, says right here, a more massive particle at the same temperature of a less massive particle moves slower. So if we have O2, okay, the mass of one O2 molecule would be 32 atomic mass units. Okay. So somebody asked me how I figured out how many AMUs was in oxygen. I'm going to show you this because you have to know this for chemistry. But if you look right up here on your periodic chart, you probably all have your periodic charts out, right? That says 15.9999. That means that each piece of oxygen mass is 15.9999 AMUs. That's the average. So like an actual piece of oxygen is going to mass 16. And then there's isotopes, which we'll talk about later. But if I have O2, that means I have two pieces of oxygen, which is 32. Do you get that? Okay. So if you look back at our notes here, we said O2 is 32 AMUs, and hydrogen, H2, which each hydrogen has a mass of 1 AMU, would be then 2 AMUs. Okay? So this is the second time I talked about this. We're going to have to do math with this stuff later. So you're going to know it by the time we get there. Okay, so now let's look at this definition of kinetic energy. Kinetic energy is expressed with this formula. Kinetic energy is equal to 1/2 mass times velocity squared. Okay? So which one of these symbols means the movement or the speed? V, right? Mass is how much it has, how many particles it's made of. V is the speed or how fast it's going. And temperature here is average kinetic energy per particle, or it's related to the average kinetic energy per particle. It's a direct relationship. There are some other numbers there that we'll talk about when you get to physics. But it's basically the speed of the particle times the mass, but it's the square of the speed. So you can see here, if we have the same temperature, and it's directly related to kinetic energy, if I have, okay, in kinetic energy, if I have a bigger mass, then I have a smaller velocity. And at the same temperature, I could have a smaller mass and a little bit bigger velocity. It's not a direct trade-off because the velocity is squared, so it has more power. It's got that square power. Does that make sense? Okay. Any questions about that? Okay, so let's look a little closer at these evidences of particle motion. So right here, diffusion. Diffusion is the process of mixing due to particle motion, and it happens more rapidly when the materials are hotter. Because when the materials are hotter, they have more velocity, right? If they have more velocity, they cover more space per time. If they're moving around faster, they can mix faster. Does that make sense? Okay. Diffusion happens more rapidly in gases than liquids since there is more space between movement and examples. So let me show you something. A mole, we'll talk about mole later in this discussion, but I'm just going to tell you a mole right now is like a dozen is 12. A mole is 6.02 times 10 to the 23rd. So if I had a mole of salt, you know, it might be as big as kind of this little piece right here of salt. That's how many pieces of salt would be. So like on the board, a mole of salt might be a little pile about that big. Actually, that might even be a little bit too big. But if I get a mole of gas, then it's going to be inside a cubic box that's like this big. Okay? So the same amount of particles in that takes up that much space in the solid, takes up this much space in a gas. So gas is basically mostly all space. But these pieces in here are moving really, really fast, so they take up a lot more space before they hit something. Or these pieces in here are just kind of wiggling and jiggling in place. They're not moving, they're locked into place. These things are actually cruising along. Like right now you're getting hit by something that's going about 300 meters per second. We talked about that earlier, right? That's why it takes up so much space for a gas. So diffusion is going to happen a lot faster in a gas than in a liquid. And liquids are really compressed like a solid too. But I have a couple videos here for you to help explain this. Yeah. Okay. Anyway, so also, we have this thing called Brownian motion. Now, this was talked about in the 17th century or 18th century, but then finally in the 20th century, Einstein actually put some numbers to this stuff. But this is crazy. Look at this. Brownian motion states particles are in constant random motion, all directions at all the time. So Avogadro's number 6.02 times 10 to the 23rd. That's how many zeros there are. So if you think of a little pile of salt has 6.02 times 10 to the 23rd particles moving, can you basically say that all the directions are taken up in that movement? Yeah, because then that's tiny. Of course there's infinite directions. So in reality they're not all taken up. But if you have 6.02 times 10 to the 23rd pieces wiggling, jiggling, bumping into each other, I'm pretty sure you're going to have most of the directions taken up. That's an amazingly huge number. That's Avogadro's number. So here's a little cartoon to help you remember. This is Toast Head talking to this guy right here. I'd love to talk to you later, Avogadro. Can I get your number? You're going to need a bigger piece of paper than that, baby. Okay, so the physical states of matter. We got solid, liquid, gas, plasma. We talked about plasma yesterday. It's lightning, fluorescent bulbs, right? Plasma ball, fire's probably got some plasma. Stars are all plasma, mostly plasma. Look, here's kind of what solids look like here. They're all kind of in a structured, rigid fashion. And then these things are just like wiggling and jiggling in place, kind of. So their movement is wiggling and jiggling in place. The liquid is, notice how the liquid is very close. The particles are very close, just like a solid. They're very similar as far as how close they are to each other. These things are wiggling and jiggling in place too, but these can slide past each other. So you might find this particle down here minutes later, where a solid, it's locked into place. And then a gas, this doesn't even do it justice. This container should probably be, like this big, at least to have that many particles of gas in it. If you're kind of talking about all the same amounts. Okay, so solid, liquids, and gases. Now, I know you guys have talked about that before. How do you change a solid to a liquid and a liquid to a gas? You add heat. We do have to talk about heat and temperature. So if temperature is the average kinetic energy of the particles, heat then, this is not on the notes, but you should write it in. Heat is total kinetic energy of substance. So that would take in all the little individual pieces and all their movement and adding it together. So like I'm going to ask you, what has more heat? A steaming hot cup of coffee or the YMCA swimming pool, the cold one? What has more heat?
Coffee.
That's what everyone says. Coffee, but that's not right. Because the coffee might have, an amount of particles that are this big, and they're moving around really, really fast. So that has a high temperature, because temperature is average per particle, but there's not much of them, like Bailey was saying. Where the swimming pool has, all these particles, they're moving slow, but when you add all their energies together, it's much, much more than just a few moving really, really fast. So heat is the sum of all the little energies of all the particles where temperature is the average per one particle. Any questions about that? Okay, so that's heat and temperature. And these notes are pretty self-explanatory. I think you've seen them all before. The only difference is when we talk kinetic theory, you need to know that we're talking about movement. And a lot of times they talk about two different kind of forces when they're talking about kinetic theory. And it's an attractive force and an opposing force. So the attractive force, and I don't know if this is the right way to talk about it exactly with forces, but the attractive force then would be what's locking it into the crystalline spot. And then the repulsive force would be what's repelling it. So if you think of an atom, we know that there's positives in the middle, in the nucleus, and there's negatives on the outside, right? And then the next atom is going to have positives and negatives on the outside. So the fundamental law of electricity is opposites attract, right? Remember we talked about that, didn't we? So this proton has an attractive force to these electrons of the other atom, and the electrons have that same force. But on the other hand, at the same time, these electrons of one atom are getting repelled away by the electrons of the other atom. So these are the two forces that they're calling attractive and repulsive. This really comes down to electrostatic forces. Okay, any questions about that? You sure? Okay. And a solid, basically this is just like saying solid's going to have low kinetic energy, it's going to have high attractive forces. A liquid's going to have higher kinetic energy, a little bit lower attractive forces, and then a gas is basically governed by the repulsive forces and has very high kinetic energy. Okay, so there's two kinds of solids here, and then the densities too. You can read those notes and study those. It's all plain and simple stuff. This is what we would call a crystalline solid. Okay, so this guy right here is a crystalline solid. And these are some common crystalline shapes. Okay, this shows some common crystalline shapes. You'll study that in chemistry for sure. And then we get down to the amorphous solids, which are going to be a little bit different. So an amorphous solid, and you can see down here, there's a little bit of kind of shows crystalline solid is going to have this regular repeating pattern all the way through. This polycrystalline, poly means many. So you can see that there's many different kinds of crystalline solids added together. That's what this polycrystalline means. And then amorphous, there's hardly any well, there isn't a pattern. And like here's glass, for instance. There's no pattern to it. And that's called an amorphous solid. Anyone like to eat amorphous solids? I know some of you do. And this is kind of that one, right? Laffy Taffy is kind of an amorphous solid. We're going to do a little lab with some like kind of solid liquid stuff tomorrow too. And then we have liquids. So that's liquids are going to have higher temperatures than solids of the same substance. They're going to have less attractive forces. They're going to have high density, just like a solid. And one of the cool things that we know about liquids here is this this low compressibility. So we use those in hydraulics because you can't really compress a liquid anymore, but it still can change shapes. So it's nice like a solid. It's not compressible, but you're able to change shapes, so you can use them in hydraulics and other types of situations. So we talked about viscosity already, right? The measure of the attractive forces in liquids. The more thick a liquid is, the more viscous it is. Okay, I'll let you watch this video here while I get this little demonstration ready. That's it for the note.